In this video, I will provide a quick explanation of how to use Prim's algorithm to find a minimum spanning tree in a graph. So let's start with a quick definition. A minimum spanning tree is a subset of edges in a connected weighted graph that connects all vertices with no cycles and has the minimum total edge weight. So one way to find a minimum spanning tree is to use Prim's algorithm, which uses the following process. Step 1 is we select any vertex to start with. Step 2 is choose the edge with the smallest weight that is connected to the vertex you just chose as the first edge in the minimum spanning tree. And step 3 is continue to choose edges with the smallest weight that are connected to the existing minimum spanning tree, assuming they don't form a cycle with the previously chosen edges. So let's consider the following graph down here, and let's see if we can use Prim's algorithm to find a minimum spanning tree for this graph. So step 1 of the algorithm says select any vertex to start with. So it doesn't matter which vertex we choose. For this example, let's just say we choose vertex A. Step 2 says choose the edge with the smallest weight that is connected to the vertex you just chose. So if we consider the 3 edges that are connected to this vertex A, we can see that the one with the smallest weight would be this edge right here because it has a weight of 2. So this is going to be our first edge in our minimum spanning tree. So let's go ahead and draw that over here. Okay, so our current minimum spanning tree contains vertex A, this edge right here, and vertex C. Now, step 3 says continue to choose edges with the smallest weight that are connected to the existing minimum spanning tree, assuming they don't form a cycle with the previously chosen edges. So now if we consider all of the edges that are connected to vertex A and vertex C, which one has the smallest weight? Well, we can see that it would be this edge right here because it has a weight of 2. That's the smallest edge that is connected to A and C. So we'll go ahead and add this edge to our minimum spanning tree. Okay, so now here's what our minimum spanning tree looks like. So now let's choose the next smallest edge that is connected to either vertex A, C, or D. We can see that would be this edge right here. So let's add that to our tree. Okay, so now we've added this edge to our minimum spanning tree. Now let's pick the next edge that is the next smallest that we could add to our tree. So we can see that we have a few choices here. These 3 edges all have a weight of 2, so we can pick any of them that we want to. So let's just go ahead and pick this edge right here to add to our minimum spanning tree. Okay, so now we've added that edge to our minimum spanning tree. Now what would the next smallest edge be that we could add? Well, again, we have an edge right here with a weight of 2, and another edge right here with a weight of 2. But what we'll notice is that if we add this edge right here, we would create a cycle right here between these 3 vertices, which is not allowed in a minimum spanning tree. So we cannot add this edge to our minimum spanning tree. So that means we must choose this edge. So let's go ahead and add that to our tree. Okay, so we went ahead and added that edge. Now, what's the next smallest edge that we could add to our minimum spanning tree? Well, there's an edge right here with a weight of 3 and an edge right here with a weight of 3. But if we chose this edge right here, this would form a cycle between these 3 vertices, which is not allowed. So we can't choose that edge. So that means we must choose this edge right here to add to our tree. So let's go ahead and do that. So once we add this edge to our minimum spanning tree, we'll see that all of the vertices are now connected and there are no cycles. So this is our final minimum spanning tree, or we'll abbreviate it as MST. And we can find the weight of this minimum spanning tree by just adding up all of the weights of the edges. So when we add all those together, we find that the total weight is 12. So what we just did is we found a way to connect all the vertices in the graph without using any cycles and with using the minimum total edge weight possible.